Okay, we will start this lecture with an example that we did previously, and then we will take this example a little bit further. So let's define a random variable x to be the outcome when you throw a die. Then in the table we have the probability distribution of x. So x can take on the values 1, 2, 3 up until 6, and each of these values has a probability of 1 over 6. And then we also have the probability distribution in a graph. We then took all possible samples of size 2 from this population, and we calculated the sample mean for each of these samples, and we've set up the sampling distribution of x bar, and that's given at the bottom of this slide. And then also the sampling distribution in a graph form, and we see that it's symmetrical and almost bell-shaped. Then what we also saw is that the mean of the sampling distribution is equal to 3.5, which is the same as the mean for the population. And the variance of the sampling distribution is equal to 1.46, which is the same as the variance of the population divided by 2. So now we're going to take this example a little bit further, and we're going to repeat this empirically for different sample sizes. Okay, so what you see here on this slide is that I have selected empirically 20 samples, that's the number of repetition, 20 samples of size 2, sample size 2. And for each of these 20 samples, I have calculated the sample mean, and the empirical frequency distribution of these sample means is given by the blue bars. The transparent bars give us the distribution of x, of the population. So what I'm going to do first is I'm going to increase the number of repetitions. So I'm going to increase the number of samples that I take. So here you can see if I increase the number of samples, then the distribution of the sample means, the sampling distribution follows this almost bell-shaped distribution. And what I want you to note here is that the mean of the sampling distribution is the same as the mean of the population, namely 3.5. So what I'm going to change next is I'm going to increase the sample size. Okay, so now I have 3,510 samples of size 20, and for each of these samples I calculated the sample mean, and the sampling distribution of these sample means is given in the blue. And again, you will see that the mean of the sampling distribution is the same as the mean of the population, 3.5. But the important thing to note here is now that the variance of the sampling distribution dramatically decreased. So we see that for different values of n, the sample size, the mean of the sampling distribution is the same as the population mean. However, the variance of the sampling distribution decreases as my n increases. What we also saw is that if n increases, the sampling distribution of x bar becomes increasingly bell-shaped. And what we have seen in these simulations is summarized in the central limit theorem. Now, the central limit theorem is one of the most important theorems in statistics. The central limit theorem states that if x bar is the arithmetic mean of a sample of size n from any population, with a mean of mu and a variance sigma squared, then the sampling distribution of x bar is approximately normal for a sufficiently large n, for sufficiently large sample sizes. The mean and the variance of the sampling distribution of x bar is given by, and the mean of the sampling distribution is the same as the mean of the population, and the variance of the sampling distribution is the variance of the population divided by n. Now the standard deviation of the sampling distribution is just the square root, so that will be sigma over square root n, and we call this the standard error of the mean. So we can conclude by looking at the summary of the sampling distribution of the mean. The mean of the sampling distribution is the same as the population mean. The variance of the sampling distribution is the population variance divided by n. So the larger the sample size, the smaller the variance of the sampling distribution. The standard error is just the square root of this variance, so that will be sigma over square root n. If the population follows a non-normal distribution, then x bar follows an approximate normal distribution for sufficiently large sample sizes. We usually say for sample sizes greater than 30. And this is the same as what we had in our example. Our population was a discrete uniform distribution, and we saw that as we increased the sample sizes, the sampling distribution became more and more normal. Now, if the population follows the normal distribution, then the sampling distribution of x bar will follow the normal distribution for any value of n. So n need not be sufficiently large if the original population distribution was a normal distribution.